In 4.2, we're going to look at vector spaces. Now, we've already dealt with some vector spaces such as R2 and R3, and we've talked about R4 and other larger dimension vector spaces. But the idea of a vector space, the definition actually encompasses more things than just those. And so we will we'll get to the formal definition of it pretty soon. But before we do that, we need to talk about the concept of closure. So first up, think about the positive numbers. If you pick any two positive numbers and you add them together, the result is another positive number. And we describe this by saying that the set of positive numbers is closed under addition. So here are several more examples. The positive numbers are closed under multiplication because if you take any two positive numbers and multiply them together, you get a positive. The positive numbers, though, they're not closed under subtraction because it's possible to find two positive numbers, that when you subtract, the result is no longer a positive number. The real numbers are closed under multiplication because if you multiply any two real numbers, you get a real number. But maybe I should have put this in here. The negative numbers, they are not closed under multiplication. And that's because if you take two negative numbers and multiply them together, you get a positive number. Let's see, what about this? The non-zero real numbers. So the non-zero real numbers, they're closed under division because if you take any two numbers and divide them, I shouldn't put a zero there. If you put any number up here and any number down there, what you get is going to be a real number. Now this is with the caveat that these are non-zeros. And the non-zero integers are not closed under division. Because if you take a number like 3 and divide it by 7, what you get out of that is not an integer. All right, so let's look at the definition of closed. We've got two different definitions here. One is closed under a given operation, and the other one is closed under scalar multiplication. We say that a set S is closed under the operation star if for any two elements x and y from S, if you do x star y, the result is defined and also in S. And for closed under scalar multiplication, a set's closed under scalar multiplication if for every element in S and any scalar you pick, then C times X is also in S. So we've got a fact down here that says Rn is closed under vector addition and scalar multiplication. And in fact, Rn is going to be a vector space. But let's play with this for a moment. Let's say that we're looking at any two vectors in R2. I take this vector and this vector, and I'm just drawing two arbitrary vectors. Any two vectors in R2, you add them together, the result's in R2. And also, if you take any vector and multiply it by a constant, all that's going to do is scale the vector and maybe reverse its direction, but it's still in R2. So R2 is closed under vector addition and scalar multiplication. And the same holds true for all Rn. There are some examples I want to look at. Let me look and see if I have already put them in here. Yeah, the examples I want to talk about are we're gonna get to later, so I'm not going to make them up right now. But anyway, this is the concept of closure, and we're going to use that when we define a vector space. Now, vector space has a really long formal definition. It says, let V be a set on which two operations, vector addition and scalar multiplication, are defined. If the listed axioms down here, if all this stuff is satisfied for every U, V, and W in V, and every scalar, C and D, then this is a vector space. Now, this is a really long definition, and the reason it's so long is because they're talking about vector addition and scalar multiplication here being defined. Well, if you want to get really abstract, you can define these in different ways. But if you use the standard definitions for vector addition and scalar multiplication that we've been using, then really the only things that are important is this down here. A vector space is a set of vectors that is closed under vector addition and is closed under scalar multiplication. So as far as we're concerned, this is the definition of vector space that we're going to use. So some examples of important vector spaces are these guys. We've already talked about some of them. The real numbers, that forms a vector space. If you think about it, that makes sense. It's the set of all vectors that live on the number line. You take any two of these guys and add them together, you're still going to have a real number on the number line. And if you take any of those and scale them by any amount, it's the result is still going to be on the number line. Let's see, my cat is right there. And the same is true for R2, for any Rn. And we've got a couple over here that are a little more abstract. The set of all polynomials. If you add two polynomials together, you get another polynomial. And if you take a polynomial and multiply it by some coefficient all the way across and distribute it out, you've still got a polynomial. And also Pn. That's the set of all polynomials with degree at most n. The idea there is, let's just play with n equals 2 for a second. If you take a quadratic polynomial, 3t squared plus 2t plus 4, if you add it to another quadratic polynomial, then the result's going to be a quadratic polynomial. Now, why do we have to say at most n? Why can't we just say n? It's because if you take say, 3t cubed plus 5, and you add minus 3t cubed plus t squared, these are both cubic polynomials, but when you add them together, you get a quadratic polynomial. So the set of all polynomials with degree at most n, that forms a vector space. And also the set of matrices, the set of m by n matrices, that forms a vector space. So that's the definition. I want to do some examples of figuring out if a given set of vectors is actually a space. And we'll do that in the next video.